All right, section 4.3 is features and limitations of the least squares regression line. There's 5 objectives in this section. I'm not going to take the time to read them all individually. The first one, though, I think is really important. That is understanding the importance of avoiding extrapolation. Extrapolation is what you do when you use this least squares regression line to predict values that go beyond the values of your data set. You don't want to do that because considering this data that we had for the houses, what if at some point this linear relationship didn't hold? Let's say as our square footage got bigger, a price kind of started leveling off because people are only willing to pay so much for the house no matter how big it is. It could give you a bad result if you use the line that did this with your data that went beyond the data sets, when in reality what really was happening was your prices were kind of leveling off at some point. Then we would have this huge difference here. That's why you never want to predict beyond what the range of your data is. So we would use the minimum and the maximum values from our data set to say, okay, we're only going to predict Y values within this range of values. Avoiding doing that thing that's called extrapolation is what you do whenever you predict beyond your data set. Don't do it. Objective 2 is computing residuals and then state the least squares property. Alright, residuals are just this linear distance right here between the actual data value and the predicted value that you get using that least squares regression line. The way that we calculate the residual is we look at that difference from the actual value of the data value and our least squares regression line. It's just a difference. This you probably want to put on your formula sheet. The formula for finding a residual is just y minus y hat. For the least squares regression line for predicting the selling price from the house, and there's the equation of the line that we calculated in 4.2, we may compute the residual for that point at 2,555 square feet with a selling price of 426,000, where the predictive value we said was 413.6, by looking at the difference between the actual value, which was this value right here, minus the predicted value, which we calculated right here, and we look at the difference between those two, and that gives us then the residual value of $12,400. That happens to be the length of this line segment, this vertical line segment right here. Any questions about that? The least squares property says basically the magnitude of the residual is just the vertical distance from the point to the least squares line. Because we're looking at y minus y hat, for our residuals, any residuals that are above this line are going to have a positive value, and any data values that are below this line are going to have a negative value. The sum of the positive and negative residuals has got to be 0 unless there's some rounding errors going on somewhere. In order to get out of adding up all the residuals and getting a net value of 0, what we do is we say let's square those distances so that they're always positive. The least squares line is the line for which the sum of the squared vertical distances, squared because we need positive numbers, is as small as possible. We call this line a line of best fit. It's a regression line, linear regression line. It follows that if we square each residual and add up the squares, the sum is less for the least squares regression line than for any other line. Because if I were to take this line and shift it just slightly, well then I've just lengthened, I may have shortened this residual, but I've lengthened this one, and I've lengthened these, and I've lengthened these others. Does that make sense? Your calculator will give you that least squares regression line. It's the line that minimizes the length of these residuals. In Objective 3, we're going to construct and interpret a residual plot. Well, first we need to talk about what a residual plot is. A residual plot is a plot in which the residuals are plotted against values of the explanatory variable x. When two variables have a linear relationship, the residual plot will not have any noticeable pattern. Remember, when we looked to see if there was a correlation, we looked for a pattern, a linear pattern. But when we look at the residual plot, we don't want a pattern. If the residual plot does exhibit a pattern, such as a curved pattern, then the variables do not have a linear relationship and the least squares regression line should not be used. Do not rely on the correlation coefficient. Remember, the correlation coefficient was the variable r. to determine whether two variables have a linear relationship, even when the correlation is close to 1 or -1. That R just measures the strength of the linear relationship, assuming that there is one. If you have a bunch of outliers, you don't want to use the calculated value of R, even though your calculator will give you one. If you see a curve in your data values whenever you do your scatter plot, you don't want to use R. But now on the residual plot, we're looking for there to intentionally not be a pattern. So we're going to use the same data that we already have in our calculator, which is convenient. The size of the house is in list 1, that's our independent variable. The selling price is in list 2, and then in list 3 I'm going to show you how to use the formula feature to put in list 3 equals A plus BX. And we already know what A and B are here from the equation that we got in the last section. And then list 4 will be the residual, which is our Y value, which is in list 2, minus the minus the predictive value that we get in list 3. Notice here I've got just the name of my list. Here I've got formulas. Whenever you are typing a formula into your calculator, you want to make sure that you put your cursor on the name of the list, and then I'm going to populate that list with a formula. So let's go back to our data that we have on our calculator and go into our list by hitting Stat Enter. And in list 3, your cursor by default is in the position of the first data entry. Move it up to the name of the list. Our y-intercept, and I'm using the line up here for y hat, we're using this line right here. Our y-intercept is going to be 160.1939 plus 0.0992. And then for the x's, I'm going to use the numerical values in list 1, so I hit second 1. So there's my y-intercept plus the slope times the variables I have for x, and I'm using the data in list 1. Your x is going to be the data that you have in list 1. Before I hit enter, and I've just got the formula, double check and make sure that the formula is right. You're looking at this formula right here. Once you feel that it's right, we're going to hit enter and it'll populate the data. It'll populate the list with the data. And we can compare what we got in list 3 with what the publisher got, and it looks exactly the same. Any questions about that one? Yeah, mine is too. That's a rounding error. It's just a difference in rounding. Yeah, mine's 410.28. So there's a little bit of off rounding depending on what program they used and how they rounded. Now to get list 4, I go back over to the name of the list, move the cursor up so that L4 is highlighted, and I want to do my residual, which is y minus the predictive value. My predictive value is in list 3, so we do second list 2 minus second list 3. Second 2 minus second 3. And if you look down here where you've got your formula in on your calculator screen, you should say L2 minus L3, and the minute I hit enter, it populates the list with those residuals. Notice some of these are positive, some of them are negative. If I added them all together, I'm not going to get exactly 0 because there is some rounding going on here, but it'll be really, really close to 0. Now what I want to do is I want to see the graph where I plot my residuals against my x's, my list 1. This is still going to be a scatter plot, so the first thing I need to do is go back into my home screen by hitting second mode, and then I want to do another scatter plot, only now I want to do my x's, my list 1 against my list 4, which is my residuals. So we go into scatter plot, the scatter plot is selected, my x's are going to be list 1, my y's are now going to be the residuals I calculated in list 4. We change that, and now we do have to do zoom 9 again because our y values have changed, so our window has to change so that it'll display the data. So we hit zoom 9, and now we've plotted our data values, the size of the square feet for the x's against the residuals. And notice I have some residuals that are positive, meaning they're above the x-axis, some that are negative below the x-axis, but it all looks kind of random. There's definitely no pattern here. Because there's no pattern on my residual plot, that means that this is a linear set of data and I can feel confident in my linear regression line. And you can watch the video again to review how we did the residuals. But to do the residual plot, let me write down some steps right fast. To get the residual plot on the TI-84, first thing you want to do is you put your data in your list, just like we did over here. I've spelled out how to do the list. Then you're going to go back to the home screen. Then we hit second y equals and select the type of graph that you want. That's the scatter plot, where the x is list 1 and the y this time will be list 4. That's your residual. And then we hit zoom 9 to look at the residual. The publisher's also been nice enough to tell us how to do this on the TI-84 calculator, so you can print out the notes and see the notes, and they're all pretty. But you may want to put something a little more concise, such as this, on your formula sheet because it takes less space. Objective 4 is to determine whether outliers are influential. The word influential just means something that has an influence on or changes something else, so common sense comes into play here. An influential point is a point that, when included in a scatter plot, strongly affects the position of the least squares regression line. Consider a scatter plot of farmland versus total land area for the United States. The blue line on the plot here is the least squares regression line computed for 48 states, not including Texas or Alaska. Both of these states have a huge land mass. Only Alaska doesn't have a lot of farmland just because it gets so cold. They don't do a whole lot of farming up there. But in Texas, we have a ton of farmland here. And I don't know if they're counting pasture land as farmland as well, but we do have a lot of farmland. If we take Texas and Alaska out of play and we just look at the rest of the 48 states, we end up with this as our least squares regression line. If we throw Texas back into the mix and look at all the 48 states plus Texas, then it shifts the line over to here. So Texas is somewhat influential. Not a whole lot because that's not a huge shift. But if I throw Alaska into the mix down here where they have a huge land mass but not a lot of farmland, it takes our regression line and makes it almost horizontal. So I would say that Alaska is definitely an influential point because it greatly shifts that least squares regression line. This is what Alaska does. That's how Texas shifts it. Texas, I would say, is influential, but not near as much as Alaska. If you have these points that are considered outliers and may be influential, if you're doing your own research and writing up your research, you need to report the data and give the regression line both with and without that influential point. Influential points are troublesome because the least squares regression line is supposed to summarize all the data rather than reflect the position of a single point. Up here, this regression line reflects the behavior mainly of Alaska. So we would say that Alaska is an influential point. When a scatter plot contains outliers, the least squares regression line should be computed both with and without each outlier to determine which outliers are influential. If there is an influential point, the least squares regression line should be computed both with and without the point, and the equations of both lines should be reported. The last objective, I believe, is objective 5, and that is to compute and interpret the coefficient of determination. This is another variable that we get whenever we do the analysis on our calculator for the least squares regression. This is the R squared. R, remember, was our correlation coefficient. The coefficient of determination is R squared. Consider the least squares line and the line y equals y bar. Y bar is just your average value. If you have y equals y bar, it's just a constant function passing through your average value for y. For any point, y minus y bar can be split into two parts. The first part, y hat minus y bar, gives us what we call our explained difference. The difference between the central value y bar and the predicted value y hat is called the explained difference and represents the difference explained by the least squares line. The second part, this part right here, is the unexplained difference. This difference is caused by factors that are unrelated to the least squares regression line, so that would be our unexplained difference. The better the least squares predictions are, the smaller the unexplained differences will be. We measure the size of the unexplained differences by squaring them and adding them together. This quantity is called unexplained variation. The explained variation is found similarly with explained differences. The coefficient of determination is the R squared that I was talking about. When two variables have a linear relationship, the correlation coefficient R tells how strong the relationship is. That's what R does, and that's our correlation coefficient. The measure most often used to measure how well the least squares regression line fits the data is R squared. R squared is our coefficient of determination, and both of these numbers we can find on the TI-84 graphing calculator. Don't worry about how to calculate these by hand. Let's go ahead and run the linear analysis again, the least squares regression on this data that we have in our calculator. We're going to run it one more time so I can print the output here and we'll talk about it. So we go into our calculator, we hit Stat, go over to Calculate. Remember, we want to do the linear regression analysis that's in number 8. You want to make sure that your X's is list 1, your Y's are list 2, because we remember 3 and 4 we were using to get the residual. We're not using those now. Scroll down to Calculate, and this is our output. If you don't see the R and the R square at this point, that just means that you need to turn your diagnostics on, and you can look back at the 4.2 video to see how to do that. R is our correlation coefficient, and that just measures the strength of the linear relationship. R squared is our coefficient of determination, and this number, that means that 81% of the variation in the problem can be accounted for, and that's called our coefficient of determination. It's not due to just chance. You should know that extrapolation outside of the range of data should generally be avoided. Usually you only want to predict variables within the range of the given data. We will calculate the residuals and the least square regression line and the R squared on our calculator. And if we have an influential point, we need to run our data both with and without that influential point included, and then report the results of both. And the coefficient of determination here is the R square that we get when we run our linear regression analysis. And this wraps up section 4.3.